In our last class meeting, we had talked about self and mutual inductance, and we had drawn a small system that contained two coils, and we were talking about the induced voltages containing a mutually induced portion and a self-induced portion. So what we're going to do now to kick things off today is we are going to define a dot convention that is used to make the analysis of those types of systems a bit more straightforward. So let's call this go away menu. Dot convention in magnetically coupled circuits. All right, so I'm going to redraw our circuit from our last class meeting, wherein we had some sort of sinusoidal excitation applied across a pair of coils like so. So this coil has N1 turns, so this will be coil number 1. The induced voltage drop across said coil is V1, and the current flowing through coil 1 is I1. And then we have a second coil which has N2 turns. It is also excited. And the voltage drop across our second coil is V2, and the current flowing into our second coil is I2. Now, I mentioned in our last class meeting that the direction of the fluxes and all of that kind of stuff can be additive or subtractive. So we have to effectively have some information about the directions the coil is wound, whether clockwise or counterclockwise, in order to make sense of what's going on in our system. Well, that type of information is not very easily relayed on a schematic diagram. So instead, we use what's called a dot convention to figure out what's going on. So I'm going to redraw this system using a dot convention, okay? So this is just something more aligned with what you might see on a schematic diagram. And I'm exaggerating the size of this very, very simple circuit so that we can add in some pieces of information as we go. So starting with my sinusoidal excitation on the left-hand side here, now I have the terminals for coil 1, and I'm going to draw this real long like so. And coil 1 will have some inductance L1, and I'm going to choose to put a dot on the top side of coil 1. Then over here, I'm going to draw coil 2, which has some inductance L2. I'm going to choose for now to put a dot on top of coil 2. And then I'm going to indicate that these two coils are magnetically coupled by putting a double-headed arrow that points to both of the coils. And then I am also going to include some mutual inductance M, where all of these inductances, L1, L2, and M, are all measured in henries. Then I'm just going to continue and draw the remainder of the circuit. Like so. So let's put some things in place here. Once again, the voltage drop over the terminals of coil 1 is simply going to be the voltage V1. And as we learned in our last class meeting, this induced voltage V1 will have a self-induced voltage term and a mutually induced voltage term. So I'm just going to write out here L di1 by dt plus M di2. Let me erase that so it's clear. By dt, where this is the direction of current I1 and this is the direction of current I2. Similarly, we're going to have a voltage V2 over here, where this will be L2 di2 by dt plus M di1 by dt. And now we're going to talk about the relationship between where our dots are located, the positive polarity terminals of our respective voltages, and the direction of our current flow, and how those things affect the sign on both the self-induced and mutually induced portions of both of our voltage expressions. Okay. Thank you. That is supposed to be L1. Yeah, so L1 di1 by dt plus M di2 by dt. And then V2 is L2 di2 by dt plus M di1 by dt. Thank you for that. Okay. So let's scroll down here. So we have two things to look at. So the first thing that we're going to be looking at is the self-induced portion of V1. So we can say that the self-induced portion of V1 of t is assigned a plus sign if the positive polarity of V1 is at the dotted terminal and I1 of t enters coil 1 at the dotted terminal. And this is the case that we have in the circuit that I've drawn. So let me be very explicit about this. Okay. So this portion up here is literally just a short circuit. So we can see very easily that the dot on coil number 1 is on top, and the positive polarity terminal of the voltage V1 is on top. So we've met the first part of this criteria. The positive polarity of V1 is at the dotted terminal. And now we check our current, and we can see that the current I1 is flowing into the dot. So we have met the second half of our criteria. I1 is entering coil 1 at the dotted terminal. So if both of those conditions are true, then this first term right here should have a plus sign, which is what is indicated on our figure, right? There's no minus sign out in front. However, there is another condition that could cause us to have a plus sign on our self-induced portion. So the other condition is the positive polarity terminal of V1 is at the undotted terminal and I1 enters coil 1 at the undotted terminal. So effectively, if we were to change the polarity of the voltage V1 and the current I1, or the direction of the current I1, that would also give us a positive sign on this self-induced portion. These are the only two criteria on which the self-induced portion will have a positive sign. So if only one of the things is met, it gets a negative sign, okay? So if our positive polarity terminal is at the dot and our current is flowing into the undotted terminal as it flows the opposite direction, this would get a negative sign. Similarly, if we put the positive polarity terminal on bottom while allowing the current to flow into the dot, we would also get a negative sign. Is this clear? For whatever reason, this seems to confuse the hell out of you guys. So I'm trying to be as illuminating with the criterion as I possibly can be without being more of an ass than usual. So anyway. All right, so any questions on what makes the self-induced portion of our voltage have a positive sign? Fairly straightforward. Okay, so now let's talk about the mutually induced component, okay? So the mutually induced portion of V1 of t is assigned a plus sign if the positive polarity terminal of V1 of t is at the dotted terminal of coil 1 and I2 enters coil 2 at the dotted terminal, okay, which is the condition that we have based on the circuit, okay? So the first condition that I'm checking is the positive polarity terminal of V1 at the dotted terminal? The answer is quite obviously yes. Then I'm looking at how current 2 flows into coil 2. Since this current I2 is flowing into the dotted terminal of coil 2, both of these conditions are met, and so our mutual term gets a plus sign. So this is where things can get a little bit wonky because we're looking at how the voltage refers to the dot on coil 1 and how the current is behaving with respect to the dots on coil 2. We have a second condition for a plus sign as well, which is effectively just the exact opposite situation. So if the positive polarity terminal of V1 is at the undotted terminal of coil 1 and I2 enters coil 2 at the undotted terminal, then we will also get a plus sign. And then I'll just put a note here. If these criteria are not met, the term is assigned a minus sign. So let's look at a couple of circuits and see if we can't sort out how to define our induced voltages, and then how we could use those induced voltages to solve a circuit. And these first couple of circuits, until we learn a few more things, are going to effectively only be able to be solved by using a tool like MathCAD, because they are going to involve a system of equations involving complex numbers, because we're going to be working in the frequency domain because time domain sucks, as you're all aware.
If we were to do like the right circuit, would you just flip all the?
So fantastic question. So all of the criteria that we just talked about were what's going on for voltage V1, but these exact same rules apply for the induced voltage V2. You would just, everywhere that you see coil 1, replace it with coil 2. Everywhere you see coil 2, replace it with coil 1. Everywhere you see V1, replace it with V2. Everywhere you see I1, replace it with I2. So it's the exact same conditions. Yes. Thank you for that, because I did not specify that, and it is rather important to know. Okay, so let's work 2 quick-ish examples. And by work, I mean we're going to set things up. We're not going to solve it because I don't have the time nor the mental bandwidth to show you guys MathCAD today. So let's say that we have the following circuit, where I've got a 100 angle 0 degrees volts RMS source. I have an impedance here that I'm just going to call 4 minus J2 ohms. And then I have a coil here that has an impedance of J6 ohms with the dotted terminal on bottom. Then I've got my second coil here with an impedance of J12 ohms. Dot is on top. I have an 8 minus J4 ohm impedance. A 6 ohm resistance. And our ultimate goal for this particular problem would be to find the phasor voltage V out. And last but not least, we have J4 ohms of mutual inductance impedance between our two coils. So at present, we have not defined the voltage drop across our coils or any of the currents flowing into or out of our coils or anything like that. So I'm going to define some things here. So let's start by saying that, actually, yeah, that'll work. So let's start by saying that our voltage V1 as a phasor is positive polarity on top, and let's make our phasor voltage V2 positive polarity on top as well. And let's define what is effectively a mesh current. I know your minds are blown that I'm intentionally using mesh for something. So let's define a mesh current I1. And a mesh current I2, like so. So before we get into literally any of the analysis whatsoever, the first thing that I'm going to do when I approach any of these problems is to define my voltages V1 and V2 in terms of my mesh currents. Okay. So let's start with V1. All right, so let's think about the self-induced portion of this voltage first. Okay. So the positive polarity terminal of the voltage V1 is at the undotted term. We all agree on that. And our current I1 is flowing into the undotted terminal. And we all agree on that. So what should the polarity of the self-induced voltage term be? Positive. If the positive polarity terminal is at the undotted terminal and the current is flowing into the undotted terminal, we should get a plus sign. Okay. So we're going to have positive. So I'm just going to write plus right here. Troy, how may I help you?
I was just going to say, did you put the positive on the top of the negative for both voltages just to make it easier? Or did you just pick that?
I just picked that because we're usually used to writing plus on top and minus on bottom, and I'm used to defining mesh currents as flowing clockwise. Right. Now, that being said, one easy way to do things, at least for a circuit that looks like this, would be to define your positive polarity terminal always at the dot and to define your currents always flowing into the dot. That way, everything always gets a plus sign. But it's probably going to be opposite to the directions that you're used to using in your circuit analysis. So there's potentially a little bit of drawback to that. But I'm just trying to get you guys familiar with this. Okay, so we figured out the sign for our self-induced portion. So what should the value of the self-induced portion be? Ohm's law, I times Z. So I1 times J6 ohms. Now we need to figure out the mutually induced voltage for V1. Okay. So once again, the positive polarity terminal of our voltage V1 is at the undotted terminal of coil 1. Okay. Current I2 is flowing into the undotted terminal of coil 2. So what should the sign of our mutual term be? Positive. Also positive. Its value will be our current I2 times our mutual inductance impedance of J4 ohms. So before we look at our induced voltage V2, does anybody have any questions on where these plus signs came from or where these values came from? Okay. All right, so now we're looking at induced voltage V2. So let's deal with the self-induced portion first. So the positive polarity terminal of the voltage V2 is at the dotted terminal, and our current I2 is flowing into the undotted terminal. So our self-induced portion should have which sign? Negative. Negative. Okay. So we're going to have minus J12 ohms times I2. Looking for the mutually induced voltage portion. Our positive polarity terminal is at the dot. Our current is flowing into the undotted. So our mutual term should have a negative sign as well. So it's going to be minus J4 ohms times I1. Now we would get around to doing our circuit analysis, okay? So effectively, all I'm going to do for a circuit as simple as this is simply write a Kirchhoff's voltage law equation around mesh 1 and write a Kirchhoff's voltage law equation around mesh 2 to set up my system, right? So I'll do that over here. KVL at mesh 1 is just going to be negative 100 angle 0 degrees volts RMS plus 4 minus J2 ohms times I1 plus V1 is equal to 0. So we don't even really need to worry about any of this other jazz because we know what this voltage is. We defined it in our first step. If we wanted to, we could substitute in that expression for V1 directly. But because I'm going to use MathCAD to solve this thing anyway, I'm just going to let MathCAD handle a 4 equation 4 unknown system instead of making substitutions to make it a 2 equation 2 unknown system because I'm terrible at algebra. Then we would do KVL at mesh 2. And so starting from the bottom left-hand corner, we would simply have negative V2 plus 8 minus J4 ohms times I2 plus 6 ohms times I2 is equal to 0. Solve this system. And then from here, we could say that V out is simply 6 ohms times I2. So we've got everything set up, and now we would just let the computer take care of all the math for us. So this one is a fairly easy one. And as it turns out, possibly later today, but definitely by the end of class on Wednesday, we will have developed a method that we could solve this system without the use of a computer. Okay. So now let's look at something a little bit more difficult. Actually, let me just go back up here real quick. The only thing I'm going to do here is I'm just going to add the numerical example for those of you that might want to go throw this into MathCAD and just make sure it all works out okay. So this should be 24.828 with an angle of negative 155.556 degrees volts. All right, so our second example. In this one, we're not going to have the left-hand side and the right-hand side of the circuit effectively isolated from each other, okay? Because we can definitely have two inductors in a circuit that are close enough to each other to where they may have some coupling between them. So let's say that we have a 30 angle 0 degrees volt source. Four ohm resistor like so. A J6 ohm inductance coil dot on the left-hand side. Here we'll have a minus J10 ohm capacitance. Here we'll have a positive J4 ohm coil dot on the right-hand side. Here's an 8 ohm resistor. And there is J2 ohms of mutual impedance shared between those two coils. And our ultimate goal in this problem would be to solve for this current, which I'll call IX. So I'll let you guys choose some things. So let's say, Patrick, do you want the positive polarity of voltage V1 on the left or right of coil 1? Completely arbitrary, just pick.
Left.
Left, okay. So that means that this is going to be the voltage V1. Hannah, do you want the positive polarity voltage of V2 on the left or right of coil 2? On the right. You guys are making it easy. Gabe, do you want our mesh current I1 to flow clockwise or counterclockwise? Clockwise, all right. And Tyler, do you want our mesh current I2 to flow clockwise or counterclockwise? Clockwise, okay. All right. So somebody tell me what the self-induced portion of V1 should be.
Positive I1 times J6 ohms.
Positive J6 ohms times I1. I agree with that. Thank you, Ian. Somebody else tell me what the mutual term should be. Negative J2 times I2. Okay. Anybody have any questions about those polarities or those values? All right. So now let's look at V2. Henley, could you tell me what actually, no, I'm just gonna put it up to volunteers. I'll bet Henley, you're welcome to volunteer if you want to. What should my self-induced term for V2 look like?
J4I2.
So negative J4I2. So just to be clear, the positive sign is at the dot. The current is flowing into the undot. So that's where that negative sign came from. Definitely on board with that. So negative J4 ohms times I2. All right, and then the mutual term, please.
Plus J2I1.
Plus J2 I1, right? So positive sign is at the dot, current is flowing into the dot, so we get a plus sign. And then from here, we would simply write our KVL equations and solve this as if we were doing a normal mesh. So let's just do that really quickly. So KVL at mesh 1 would look like negative 30 angle 0 degrees volts plus 4 ohms I1 plus V1 plus negative J10 I1 minus I2 is equal to 0. KVL around mesh 2 would look like minus J10 times I2 minus I1 minus V2 plus 8 ohms times I2 is equal to 0. And IX is just equal to I2, which comes out to 2.631 with an angle of negative 52.125 degrees amps. I'm trying to decide if I want to give you guys one last hard example or if I want to move on. Let's set up this last hard example, and then that'll be the last thing that we'll do today. We'll get out a little early because I got some work to do on senior design anyway. Okay. So we've got the following circuit. $60-volt source, 5 ohm resistance, a J10 ohm impedance, dot on the left, a J20 ohm impedance, dot on the bottom, a J30 ohm impedance, dot on the left, $20 ohm resistor like so. And then let's say that these two coils have J6 ohms of mutual inductance. These two coils have J8 ohms of mutual inductance. These two coils have J5 ohms of mutual inductance. So for this particular problem, we're going to have 3 different induced voltages, but only 2 different mesh currents to sort out. So it's not going to be particularly hard, but there's going to be a lot of bookkeeping that we need to pay particular attention to, right? So Slade, tell me what the polarity should be for the J10 ohm coil. Okay, so positive polarity on the left. So let's call that one V1 like so. Walker, tell me what's going on with the J20 coil. Positive on top or bottom? All right, so positive on bottom. And Landon, tell me what you want the polarity to be for the J30 ohm coil, please, sir. Left. All right. Now for our mesh currents, Henry, my apologies. Tell me if you want our mesh current I1 to be clockwise or counterclockwise. Clockwise, all right. And Caro, tell me if you want our mesh current 2 to be clockwise or counterclockwise. Clockwise, all right. So I'll just sneak that in down here. Okay, so let's sort out what's going on with V1. So self-induced term, what's it going to be? Positive J10 times I1. So because that J10 ohm coil is magnetically coupled to both the J20 ohm coil and the J30 ohm coil, we should see two mutually induced terms for this voltage. Okay, so let's start with the coupling to the J20 ohm coil. Okay, so this one's going to be the more difficult one to do. So here's how I would approach it. Okay, so I can see first off that my positive polarity terminal of the voltage V1 is at the dotted term. So what I would personally look for is the total current that's flowing into the dot on this J20 ohm coil. That way that mutual term will have a plus sign. To me, the current that's flowing into the dot is I2 minus I1. So that's going to look like J5 times I2 minus I1. Does that thought process make sense? J5. So the reason why it's J5 is because this is a mutual inductance term, so we need to be using the value of the mutual inductances and impedance. Now we've got to figure out the mutually induced term due to the coupling between the J30 ohm coil and the J10 ohm coil, right? So what should that part look like? Positive J6 ohms times I2. All right, so the voltage V1 seems to be well taken care of. So let's look at V2. So what should our self-induced term for V2 be? I2 minus I1 times J20, if we want a positive sign. I1 minus I2 times J20, if we wanted a negative sign. I probably want the positive sign, right? So because the positive polarity terminal is at the dot, if we just find the total current that's flowing into the dot, we can force that term to have a positive sign. The total current is once again simply I2 minus I1. All right. So now let's figure out the mutual term for the coupling between the J10 and the J20 coil. So what's that going to look like?
J10 ohms or J5 ohms times I1.
Positive J5 ohms times I1. I agree. And then lastly, the mutually induced term due to the coupling between the J20 and the J30. So J8 times I2. All right, I agree with that because our current I2 is flowing into the dot. And then now we've got to figure out V3. So what's our self-induced term there going to look like? J30 times I2 positive. What's our coupling between the J30 and the J10 ohm coil going to give us? J6 times I1 positive. And then lastly, our coupling between the J30 and the J20 ohm coil. Positive J8 times I2 minus I1. I agree. And now we would be ready to just use simple mesh analysis for this circuit. So KVL at mesh 1 would look like negative 60 angle 0 degrees volts plus V1 minus V2. Oops, I missed a term there, my bad. Plus 5 ohms times I1, then plus V1 minus V2 is equal to 0. KVL at mesh 2 is going to look like positive V2 plus V3 plus 20 ohms times I2 is equal to 0. And then we would solve that system for whatever it was that we were looking for, which I forgot to define. So let's call that current IX. And from this, IX is the same as I2, which should give you 0.862 with an angle of negative 51.90 degrees. Okay, so we seem to have a good understanding of the dot convention, which is fantastic because we are going to be using it for the next couple of weeks as we get into more nitty-gritty details about circuits involving magnetic coupling. So what we're going to talk about in our next class meeting is an introduction to transformers. So effectively, a transformer is just a circuit where we have intentional magnetic coupling. We are going to sort out kind of how transformers work, how they are able to step up and step down voltages, and inversely step up and step down current. We're going to talk about energy transfer, equivalent circuits for them, all of that kind of good stuff. So that'll be Wednesday's class. All right, thank you guys for your time, and I will see you on Wednesday.